I didn't work back to acids and bases. This is really important because we're going to talk about something called but please make sure you understand how to do the most. So we're going to talk about strong acids. Some are really weak and we keep the gas, and some acids like sulfuric acids are very strong. So we're going to look at something called the acid dissociation constant, and it's going to tell us if we have a strong acid or a strong base. So here's how we do the math of it. We take the molarity of the dissociated H+, its anion from the molecule, and then the molecule itself. And we're going to figure out the math of that. Remember, brackets mean molarity. Weak acids have a really small Ka, and strong acids have a big Ka value. So strong acids completely dissociate and ionize. HCl will totally break into pieces, form this and this. 100% of it will change from here to here, strong acids. And then strong acids will 100% ionize. Oh, sorry, my computer's messing up. Will completely ionize. And then weak acids won't completely ionize, so you'll have some of these still remaining in the container. And you'll have a few of these. So this small arrow is saying some of it changes here, but most of it stays in this form. That's a weak acid. Base dissociation constant can be calculated the same way with molarities. And strong bases completely dissociate, and weak bases only partially dissociate. So ammonia is an example where you have most of the reactants staying in this form, and you have a few products over here. This arrow, this unbalanced arrow that is showing that. So we can, here's some common acids and bases, so it's good to know the strong acids that we use in the laboratory and the strong bases we use, so know those. And how do we calculate that Ka? So we can figure it out by knowing the molarities, and let's try those. This is an important type of problem. So let's figure out the dissociation constant of ethanoic acid. So the KEQ looks like this, but this volume of water, this molarity, is going to overwhelm this number, so we get rid of it when we talk about Kas. So we just use this. Ka is molarity of H3O plus product, the anion product, and the beginning acid that we're using. Molarity. These brackets are all molarity. So if we have a strong acid, we go completely dissociate to products. Weak acid, some products, but some beginning acid left over. And a very weak acid, very much of the beginning acid is still unionized, and we have a little ionized. So these values are showing you some weak acid numbers that we should see when we do these kind of problems. Very, very small number. The smaller the number, the weaker the acid. And we can do KBs as well. And remember, KEQ has everything involved in the reaction, but we're going to do KB, which does not include the water molarity. And here's some molarities that you'll see in the laboratory for the type of acids and bases that we use in the lab. These are molarities. So this problem I'm going to show you is very, very important for equilibrium. It's called an ice chart kind of problem. And we're starting with this molarity was made in the laboratory. We measured the pH, and from the pH we did that anti-log math that I showed you before. And we got the molarity of the H plus that popped off of this acid. Let's figure out what the Ka is when we're done. So we know that for every one of these, we're going to form one of these, and one of those is a 1:1:1 ratio. If I know this value here, that value, then I have to know that's the same because they're a 1:1 ratio. And I've gotten rid of that same molarity of this when it dissociated. So we're going to put those numbers into that. We have to figure some of the numbers out first. So initially I made this molarity of this molecule, and I had none of these things in the container. It dissociated, and I formed this much of H+, which is equal to that much of anion, and I removed this much of the reactant. So I'm going to have to subtract these two to get the equilibrium concentration. This whole nice chart you have to get used to making. This is called the nice chart. Initial, change, equilibrium, so ICE. It's called the nice chart. So we're going to have to do this because we need to find out what we have at equilibrium, not what we started with. So if I subtract these two numbers, I get that value. I know I have this much at equilibrium and this much at equilibrium because they're a 1-to-1 ratio. And then I can just plug these numbers into the Ka formula and do the math. So try all this. Make sure you understand this problem. It's very important. How to do this ICE chart way of analyzing the problem. So these are equilibrium problems where you need an ICE chart. So please understand it. And do the math and see if you can get the value there in your calculator. So, and that value is consistent with a weak acid. Here's another one you could try on your own. And let's try the quiz. So, this is a weak acid because it ionizes only slightly. Calcium hydroxide, strong base because it has a large Kb value. So, you're going to have to do an evaluation of this problem, so pause me and then see if you can come up with the right answer. This is the ICE chart kind of problem. So you should get that value when you're done. And see if you can put these acids in order from strong to weak. And that's the answer. And then same thing with bases. See if you can put these in order of strong to weak. So you should get that in that order. So I hope you learned a lot from this. This is a really important set of lecture notes, especially the ICE chart. So I'll talk to you soon. Have a great day. Bye-bye.